How accurate is your chronograph? You can easily test it by dropping an object through it. Let's do it. To test this, we're using one of these lead balls here. They're fishing sinkers. And just under my ceiling I've rigged a little tube, and that's just so that the ball falls straight down through the tube and into my chronograph, and then we will see what the chronograph will display. And then you just need to do a simple calculation and you will know how accurate your chronograph is. So here I'm dropping the ball from my ceiling. It falls through the chronograph, and I've protected it with a bit of foam just in case it hits it. And let's see what it indicates. It's 5.9 meters per second. And as you can see, I've switched my chronograph to indicate meters per second here, and that's because it's much easier to calculate in metric units, because what comes next is calculating the true speed of the ball using this red formula here, and later in the video I'll show you how you can derive it from the principles of physics yourself. And then the only thing we need to do is compare the true speed we've calculated with what the chronograph indicated. The only thing we need now is the height from which the ball fell, and we're going to measure it now. So let's have a look. This is the top of the tube. This is from where I dropped the ball. This is where I start measuring. I'm using a laser rangefinder. You can use a measuring tape, same thing. And I measure down here to the face, 1.782 meters. But that's not all, because the measurement happens inside the chronograph. So I have to add the distance between the front of the chronograph and the midpoint between the two photosensors inside it, which comes to 70 millimeters. So I have to add 70 millimeters to the 1.782 meters I've measured before, which comes here to 1.852 meters. And now the only thing left is inserting that into our formula, 4.429 multiplied by the square root of 1.852, and the result is 6 meters per second. So 6 meters per second is the actual true speed. If I take the 5.9 meters indicated by the chronograph and divide it by this result, I come to an error of about 2%. So the chronograph indicates about 98% of the true speed. Here's the same calculation with a slide rule, just to test the result, and also because there's a lot more fun using a slide rule. 1.852 on the x square scale. On the x scale you have then the square root of it, slide it over, multiply by 4.429 roughly, and it comes to the same result, 6 meters per second. %2 difference between what the chronograph indicates and the true measured speed is of course very good. What it means is, if this chronograph indicates, for example, 300 feet per second, the true speed is just a little bit more, around 306 feet per second. What's more, I've tested this with two chronographs of the same type, and they both indicated exactly the same, which indicates to me that this chronograph is probably a pretty decent piece of kit. And now, as promised, for those who are interested, here is the science behind all this. Goodbye. This is an object, and imagine this object falls from a height towards Earth. As it falls, it will pick up speed. The longer it falls, the more speed it picks up. In other words, the speed, for which I use the letter V here, is a function of time. And the equation is simply the Earth's gravity multiplied by the time since the beginning of the fall. That's your speed. So the Earth's gravity is a constant 9.81 meter per second per second. And by the way, in the world of physics, gravity and acceleration are the exact same thing. So here, in other words, when you fall, you pick up an extra 9.81 meter per second, which is equal to 36 kilometers per hour every second you fall. What we need to know for our test is an equation for speed as a function of the height h, from which we drop the ball through our chronometer in our test later. The distance d a moving object travels is the integration of its speed function over time. If I integrate our speed function, I can use the result to replace the time t with the distance d. The end result is the speed of a falling object is the square root of the fall height multiplied by 4.429. And that, by the way, applies to any objects, like a ball or yourself if you fall off a tree. It doesn't quite work with very light objects like a feather, because they get slowed down by the air too much. Well, that's a different story. So here an example. If I want to know how fast I hit the ground when falling from 5 meters, I take the square root of 5, I use the slide rule here, you can also use a calculator, and then multiply the result by 4.429. And here it comes to about 10 meters per second, which is equal to 35 kilometers per hour.